Știi când au venit, că Cătălin a mai venit cu unul atunci când am fost la el prima oară.
Ai făcut patru Florida.
With an overview of the whole processor, we'll take a look at three types of instructions that we can run: R-type, I-type and J-type. Starting with R-type instructions, we go ahead and take the most significant bits and pass it in as an opcode to our control unit, as well as pass 6 bits as a function input to our control unit. The reason we do this, the function input, is that it will give us the correct control signals for the ALU, and the whole purpose of a control unit is to take in the opcode and return the correct control signals for the components within our processor. Since we're performing an R-type instruction, an R-type instruction has 2 source addresses and 1 destination address. By passing in the 2 source addresses, the data at those addresses are returned. We also take bits 15 to 11 and pass it into this 5-bit mux, and since reg destination is set to 1, we take those bits and set them as our destination register. Since we're performing addition, the ALU control signal will be 0, 1, 0. The most significant bit 0 determines how we won't be negating B, and the middle bit is 1, which means that we will be performing an arithmetic operation and not Boolean. So we go ahead and pass those values into our ALU, and since the ALU source is set to 0, we just straight up take RD1 and RD2 and plug them into the ALU. After we perform an operation with our ALU and add 2 numbers together, we don't need to perform any sort of manipulation with dmems, so we go ahead and go to this 32-bit mux, and since mem to reg is set to 0, we take the 32 bits of A and then we pass it in as our write data within our reg file, so we will write to our specific write to date the output of ALU. Now we're going to be looking at is I-type, specifically being branch if equal. So with the I-type instruction, we have 2 source addresses. Those source addresses holding the data which we want to compare and see if are equal. So we pass in those source addresses and the data is the return, and the data is then passed specifically into the ALU. ALU source is set to 0, so we take there a 32-bit bus. And then since we're running a branch of equal instruction, we'll minus the 2 inputs and see if the value evaluates to 0. If it evaluates to 0, then the 2 inputs must be the same. How we check this is we have this 32-bit comparator, and we check if the value is 0. If the value is 0 and the control signal and branch is set to 1, then this creates a signal that is passed into our first 32-bit mux, and we will take the B32-bit address. But where does this B32-bit address come from? Well, within our I-type instruction, the lowest 16 bits are the immediate, and this will hold the address of which we wish to branch to. We extend the sign so we can turn our 16-bit input into a 32-bit output, and we left shift it due to the fact our address in our processors occur in multiples of 4. We add the address we wish to go forward or back to with the next address, and this final output is our 32-bit B input. The instruction that we have is a J-type instruction. A J-type instruction allows us to jump to a specific memory address. How this instruction is structured is that the top 6 bits are the opcode, and the lower 26 bits are the operand, the address that we wish to go to. So the top 6 bits are passed into a control unit, and a jump signal is generated, which is passed into the second 2-bit multiplexer. And below 26 bits are passed into our left shift, so we can multiply the value by 4, as the addresses are in multiples of 4 for our program. And then the left shifted lower 26 bits are then passed in to the B source of the 32-bit mux, and the 4 most significant bits of the next address are truncated and inserted into our jump address. The control signal turning to 1 means that our 32-bit mux will take our B value, and then we will start to perform whatever operation is within the instruction that's within that new memory address that we have jumped to.
I'm gonna explain how our unit in the processor works. This is our control unit. It takes two 6-bit input which came from read-only memory. So op input is opcode input, so it goes into our main decoder. It directs operation of unit. So they're gonna be a single bit output, which is 0 or 1, and this indicates what to do to the processor. Especially there is a ALU op output which feeds into our ALU decoder, and these inputs feed into our 3-bit multiplexers, and it generates the output, which is ALU control. This is 3-bit output, and this output feeds into our ALU. ALU is an arithmetic logic unit, which is a digital circuit used to perform arithmetic and logic operation. This takes two 32-bit inputs, which is D and C, and also the 3-bit input which came from control unit. So this 3-bit input controls which operation that ALU should perform. So if this 3-bit input is 000, it conducts AND operation, and when it is 001, it performs OR operation, and when it is 010, it performs adding operation, etc. So there is two output from ALU, which is one 32-bit output and one single bit output, C out. So this 32-bit output feeds into our comparator and 32-bit multiplexers. This is our comparator. And comparator takes two 32-bit inputs and produces a single wire output that is set to 0 if the input are not equals, and 1 if they are equal. This is our waveform of the ALU. There is two 32-bit input, which is C and D, and one 3-bit input, which is F. This directs what operation to be done by ALU. And there is 32 output Y. So here I put 10 10 10 10 and so on as an input of C, and all 1 here, as you can see, all 1 here again, and 10 10 10 10 and so on. So here 010 means adding, so this will conduct adding operation. So these two output will be 101010, which is equal to input of C because the input is all 0. And here, this will be 101010 and so on, and 001 at the end because it adds all 1 from 101010. Here 001 means OR operation, and since here's all 0 and here's all 1, we'll get all 1 output. Okay, so 110 means subtraction, so this output will be 0 because subtract all 1 and all 1. Here will be 0 1 0 1 0 1 0 1 and so on because it subtracts 1 0 1 0 1 0 from 1 1 1 1 1 1. And this output will be all 1 since it subtracts all 0 from the all 1. Okay, let's check if it works or not. Okay, as we expected, this is 1 0 1 0 1 0, and here 1 0 1 0 1 0 and 0 0 1 at the end. And here you can see everything is 1 from the OR operation, and here apparently everything is 0. Here 0 1 0 0 1 0 1, it works properly, and the last one will be all 1. Yep. So this is our demonstration of waveform to ALU.
So this is some pseudocode for a square program. We have 3 registers, T1, T2, T3. T3 will hold the value that I'm squaring. T2 will just be a count of how many times I go through a loop. And T1 will be the actual squared value that I'll display onto the FPGA. So while true, while forever, if T2 is equal to T3, the reason I have this check and the reason I have a count of how many times I go through a loop is due to the fact how to square a value n, you have to add n to itself n times. The reason we have to do this is that within our operations, the only operation that we have is addition. So I keep doing that, and once T2 is equal to T3, I save a value to this certain address, which will display the value onto the FPGA, reset T1 and T2, and then go on to the next value that I wish to square. So here's the actual assembly code that was converted to machine code to be ran off the ROM on the processor. So we initialize T1 and T2, we set them to 0, and we have T3 and we set that initially to 1. We keep looping and adding the value to itself, and then once T2 is equal to T3, I reset. I save to this memory location, which in turn will display the value onto the FPGA. I set T1 and T2 back to 0 and increment T3 for the next value to be squared. So here's the assembly code converted to machine code for the counter program. So we have 2 registers, T1 and T2. T1 is initialized to 0 and T2 is initialized to 9. At first we display the value onto the FPGA, we increment the value and keep looping and incrementing the value until T1 is equal to T2, and that is when the count is equal to 9. Then we reset, set T1 back to 0, and go back to looping and displaying the values 0 to 9 over and over.